When the terms of a sequence approach a value, then we say the sequence converges. So it converges when the terms approach a value. An example is we could look at that example we had before, the sequence n over 3 to the n minus 1. If we look at those values, as n gets really big, my term a sub n goes to 0 because 3 to the n goes to infinity a lot faster than n does. So I say the terms are converging in this case. The definition, a limit of a sequence we have here, we let L be a real number. Then we say the limit of a sequence, the sequence we're talking about is, we always write it like this, is L. And we write it, the limit we write as this. The limit as n approaches infinity of a sub n equals L. So L is our limit. And then we also have to say that for each epsilon that's greater than 0, there exists some m also greater than 0, such that the absolute difference between the nth term and my limit is less than epsilon whenever my nth term is bigger than that number m. So it has to be significantly large. If the sequence, if the limit exists, so if the limit L exists, then we say the sequence converges to L. And if it doesn't exist, we say it diverges. So when it doesn't exist, the limit does not exist. I have a theorem, the limit of a sequence, and I'm going to let L be a real number. And f be a function of a real variable and such that we know the limit as x goes to infinity of f of x equals L. And if I have a sequence an where the function evaluated at n equals an term for every positive integer n, then we can also say that the limit as n approaches infinity of a sub n is L. So this is important. This is very strong if we can talk about a function. Now the function of n is an. That means just the list of those terms. But it's very important to note that the converse is not true. So if the sequence has a limit, it does not necessarily the function has a limit.